So we have a bunch of dot plots here that are stacked up, A through G. It looks like these are daily high temperatures in June, July, and August for cities A through G. And the questions at the bottom of the page are asking, what are the differences between, and it'll give you like 2 or 3 to look at. And so you might be able to see the differences, but what you are needing to take into account is what language you should use in statistics to describe the differences that you see. So I'm going to start by playing an AP video. Give me just a second to get there. Oh, cool. I had it pulled up from this morning. And let's see. This is like 6.5 minutes. So we're going to learn some vocab here in this.
Describing the distribution of a quantitative variable. So let's start with what we will learn and 2 questions that we'd like to try and answer in this video. Number 1, what are the important characteristics to discuss when describing the distribution of quantitative data? And 2, what are the best ways to discuss the important characteristics when describing a distribution of quantitative data? So we're going to do this through an example, one that you're already familiar with, the Flint water crisis data. If you recall, city officials measured lead levels in 71 water samples from Flint residents in January to June 2015. Here are the data from the 71 samples. And in the last video, we talked about graphs that we could use to display the data. And so, of course, I've chosen my personal favorite, the dot plot here, to represent the data. But here's what we're going to try and do in this video. We want to be able to describe the distribution of lead level for the 71 water samples in Flint. So how do we do that? How do we describe a distribution of quantitative data? And there are 4 important characteristics that you have to include in your description.
Let me pause right there. You guys, there is almost 100% guaranteed going to be a free response question on the AP exam where it gives you 2 distributions and you have to describe them, compare them to each other. So this is a very, very important lesson. And what he's about to tell you is on page 2 of your notes. Kind of in the upper middle part of the page, the question that says, how do you describe a distribution of a quantitative variable? He's answering that right now. If you'd like to go ahead and start writing. How do you describe a distribution of quantitative variables?
Number 1 is the shape of the distribution. Number 2, the center of the distribution. Number 3, the variability or the spread of the distribution. And then number 4, the unusual features.
So I always use the acronym SOX, but so for shape, and then the unusual features, I just say, describe outliers or gaps that you see. So that's the S and the O. The C is center. And then the last S in SOX for me is the spread, which technically we're talking about variability there. But it doesn't matter if you want to use the acronym to help you remember. I'll put that in the notes when we get there. Or if you want to just kind of jot these down right now, that's up to you, okay? This is just a working document. You can change anything you want to later.
So let's take a little bit closer look at each one of these 4 characteristics, starting with the shape. So here are some options of vocabulary terms that you have to use to describe the shape of a distribution. The first one is a distribution which is symmetric. And that means that the left side of the data is essentially equivalent to the right-hand side of the data.
You can sketch these at the top of page 2.
That would be a symmetric distribution. Now for a skewed left distribution, you're going to see a cluster of values here on the high end, but then a big long tail going out to the left. So the left tail is much, much bigger than the right side of the graph.
You can just draw sticks instead of the
there, so we would call that
stacks of dots
skewed
if
left.
you want to.
For a skewed right distribution, you're going to see that the right side of the distribution is much more drawn out than the left side. Now, some other terms that you can use here is distribution can be considered unimodal if it has a single peak here, whereas it is bimodal if it has 2 peaks. You'll notice a peak here as well as a peak here on this distribution. And then the final term you can use is the idea of a uniform distribution, which means that you have just about the same frequency or same number of values for each value on the x-axis there.
I'm just going to pause and give you a second to sketch those down. At the top of page 2, it says Briefly illustrate the following distribution shapes. And he's got them in dot plots. This could apply to stem plots. It could apply to histograms. You'll see histograms all the time. Box plots kind of have there's a little bit more difficulty, like with the shape of a box plot. You will be able to see if there's a skew, but that's as detailed as you could be there. So again, as you're copying these down, always be listening as you're writing. Symmetric is just exactly what it sounds like. There's some symmetry there. Now, that symmetric that he's got up there, that's in a perfect world. That is perfectly symmetrical. You can use words like roughly symmetric or approximately symmetric. You don't have to be like spot on. Give yourself a little bit of leeway there in free response. If it's not exactly symmetric, say something like roughly symmetric. Skewed to the left and skewed to the right. I want to make sure you understand right now that skewed to the left, we call that a tail. If you look at this skewed to the left, the data kind of trails off to the left. There's a tail going out to the left-hand side. That's why it's skewed left. Skewed right has the tail on the right side. And then another thing that you need to make sure, and that this was added in 2020 to the course and exam description, is when you're describing shape, make sure you say, if there's one peak of data, it's unimodal, uni meaning one, bimodal if you see two. Uniform, again, the one that he has on the screen, that's in a perfect world. It is literally straight across. You might see a uniform distribution where some of the stacks are slightly taller, but if it's generally looks like it's pretty much the same across the board, you can say roughly uniform or uniform, okay? So that's shape. Let's see what else he's got going on here.
So that takes care of the shape. Let's move on to the center. And here's the question that we're trying to answer when it comes to center. Which value in the distribution best describes the typical response? And then for variability, the question that we want to try and answer is, are the values in the distribution packed close together, or are they more spread out? Now in this video, we're going to talk fairly generally about center and variability, but then in the next video, we'll be much more specific in the way that we refer to center and variability. Now the fourth characteristic is unusual features. And you have a few things to look out for here. The first is outliers within the distribution. And usually that's going to be a value that clearly doesn't fit with the rest of the values, much, much higher or much, much lower than the rest of the values. The other thing to look out for, and these often come together, is gaps and clusters. So you'll notice in this distribution that there are two clear, distinct clusters with a gap in between those two clusters. So let's go back to the Flint water crisis data and see if we can describe the distribution.
I'm going to pause it. Let's do this together. What shape does that dot plot of data take on? Skewed. Okay, now, I used to get confused because, look, most of the dots are on the left. So you might think, oh, it's skewed to the left, but it has to do with the tail. Look at the kind of where it would trail off. There's an outlier way down there at 104, which is going to pull something we're going to talk about later, is going to pull something in that direction. So this is actually skewed right. Is it unimodal, bimodal, or uniform? Does it have one clear peak? I think it does. So you need to say unimodal. Okay, don't just tell about the skew or symmetric. Tell how many peaks it has. Okay. What about, let's see, socks, outliers? Do you right now, before you know anything else about outliers, do you think there are some possible outliers? Yeah. That's how you would word it. Until you prove it mathematically, and there is a way to do that, until you prove it mathematically, you have to use verbiage like, there are possible outliers at, where do you think they are? 104, yeah, okay, possible outliers at 104, maybe even the 42, 41, 42-ish right there. Those could be possible outliers. They're just going to be a big departure from the rest of the data, okay? I don't think, gaps, I think in this one there is a very large gap between the 41, 42-ish and the 104, so I would probably say that. What about, well, you don't really know about center yet. And then, is this data really spread out or is it closely packed together? Most of it is packed together, but unfortunately that outlier comes into play, that possible outlier. So I'm going to show you how to specifically talk about variability in just a second. Let me skip ahead and see what he does here. Unimodal, strongly skewed. Don't worry too much about the center right now if you're wondering how he got that 3 to 4 parts per million. Variability, he just gave them minimum and maximum, which essentially is like a range, but we're going to be even better than that here at the end of these notes. Okay, and I think that's a good place to stop the video. So let's look at page 1 of the notes. Let's see if we can use those vocabulary terms when you're comparing some distributions, which again could be dot plots, histograms, any sort of graph of data here. Number 1 says, what's the most important difference between cities A, B, and C? So these here at the top. What I am noticing is that they all have the same exact shape. It's like the same exact dot plot, but they've been moved. It looks like they've just been scooted around. And so I want to tell you that really the most important difference there is not how much they're spread out, because they're all spread the same, they all have the same shape, but here it would be the center that's the difference. Because where the kind of middle of the data is right now, this kind of blob of dots here, is higher for city A, it's lowest for city B, and then city C is kind of somewhere in the middle if you follow it down to that horizontal axis. So I would probably write the answer to number 1 as the most important difference being center. If you want to add to that and just put a little note, they all have the same shape, they all have the same variability. It's the center that's different. A has the highest center, B has the lowest center, and C is somewhere in the middle. Number 2, what's the most important difference between cities C and D? C and D look wildly different. So shape here, I know it's really hard to tell, but the shape would actually be pretty similar because shape is just talking about, is it unimodal? There is one single peak. They're both, I would say, roughly symmetric. It is hard to tell when the data is more spread out. There's a little clue for you. But these both actually, if I just describe the shape, I would almost write the same exact thing for both of those. So what do you think is different then if you know it's not the shape? The variability. Which one has a higher variability? D does, because it's more spread out. And so in your free response question on your AP exam, and I'm going to discuss this in the notes later, you'll have a place where you write it down. But when it asks you to compare, you need to use comparison words. Don't just tell me about C and then tell me about D as 2 separate explanations. Compare and say the variability of D is higher. It's more spread out. So we're going to put the answer on number 2 as variability. And until you kind of get used to what that means, you can kind of interchange it with the word spread. What are the 2 most important differences between D and E? That's interesting. So what do you notice is kind of weird about E? It's really packed closely together, and then there are these 2 points that are wildly way out here, departed from the data. I'm thinking those are definite outliers there. But until we can prove it, we're going to say possible outliers. So I think the unusual features are different. I want to mention something. What do you think about the variability of these graphs? What did you say? You think they have a different variability, or would they be technically the same?
Maybe the same.
They would probably be the same right now if our understanding of variability is like lowest to highest data point. Well, they both have the same minimum and the same maximum. Now we'll learn later how better to describe variability, okay? But right now, I would say the most important difference is going to be those unusual features or possible outliers on City E. City E has possible outliers. I would be shocked if those were not a low and a high outlier there. And then let's compare C, F, and G. C, F, and G. So just stare at those for a second. Oh, that one's not too bad. What's the main difference there? Shape. Shape, yeah. Shape in general. Now, if you had to be a little bit more specific, what shape would you assign to city C?
Symmetrical.
Symmetric, mostly symmetric, roughly symmetric. What about city F? And if it helps you to kind of see the tail, okay, eventually we're going to start to talk about curves, distribution curves. So you can kind of start looking at graphs that way. You can see clearly that the tail is over here to the right, so this would be skewed right, and G would be skewed left. So I think the most important difference there is going to be the shape. So that's just kind of an overall, it's really good to look at those, just kind of get comfortable with that terminology until we learn how to be more specific. All right, you can turn the page. Hopefully you kind of had a moment to sketch out symmetric versus skewed left and right, unimodal, bimodal, uniform. Instead of the stacks of dots, you could have just drawn little sticks to show yourself, but make sure you've got a really good sketch of those. And then let me just show you what I wrote in case you want to add anything to this section of your notes. But again, these are your notes. I just use the acronym SOCS, S-O-C-S, so I don't forget when I'm needing to describe something in a free response to address all of these parts. Shape, outliers or gaps, center, which we're going to talk more about today. Your options there are going to be mean or median, depending on what the distribution looks like. And then spread, variability, and that will be the lesson that we cover the next time I see you on Thursday. So don't even worry about writing down the options yet. You'll learn about that later. Okay, the two most important things to remember when you are asked to compare distribution. Actually compare. Use comparison words. Say things like higher, lower, bigger, smaller, more spread out. And then some of you kind of learned on the free response, some of you did an excellent job, and some of you that you only got points taken off of your free response last time because you gave me a beautiful answer, but it was too generalized. You always need to add context to the problem. So I know that on the first page, those were just called cities A, B, C, D, E, F, and G, but you would need to be really specific if you were comparing two of those, and you would need to say something like, city A has a higher center temperature in June, July, and August than city B. So give it some context. Use variable names, not just group names. Don't just say the first graph, the second graph, the distribution on top. If they call them distribution A and B, don't stop there. Be descriptive. Okay, now we are going to practice making a stem plot. And the most important thing to remember when making a stem plot is to label the variable, tell me what it is you are graphing in your stem plot, and then I underlined include a key. Stem plots are completely useless without a key because they could be representing decimal values, they could be representing, I guess, technically fractions, integers, numbers in the hundreds. You never know unless there's a key. So I have it in my notes to watch a little video here. Let's see what is important in video 151. I thought there would be an easy way to navigate. Apparently there's not. Alrighty. 151. dot plots. He's going to take the Flint water data here and make a stem and leaf plot. So you can just kind of see. You have made these before.
Dots get tinier and tinier as you have more and more values there. So that is a slight disadvantage to the dot plot. Another type of display you can use for the data is a stem and leaf plot, which looks like this. And what you'll see here is that each value is represented with a stem, which is the value to the left of the vertical line, and a leaf, which is the value that you see to the right of the vertical line. So for example, the number 104 is represented with 4 as the leaf, and then 10 as the stem there. Now sometimes, one of the stems ends up having lots and lots of values, like we see here with the 0, and it actually makes sense to split that stem into 2 zeros, where the first of them is going to take the 0 through 4, and the second one is going to take the 5 through 9, and that would look something like this.
Okay, let me pause for just a second. This original stem and leaf plot that he made of the Flint water data, okay, it's got the key over here of how to read it, but this would be a pretty inappropriate way to display the data because look at how long that first row of numbers is. So there's something called a split stem plot, and it looks like this, where you just take the stems and you split them. And so what he's saying is he's going to take all the digits 0 to 4 and put those on the top line, and then 5 to 9, if the last digit is 5 to 9, it'll be on the second row there, okay? So he split all of the stems, split stem.
So you'll notice the split stems here for each one of the values. Now let's talk advantages and disadvantages of the stem and leaf plot, which is going to look very similar to what we said for the dot plot. As far as the advantages, number one, you can actually see every single individual value, all 71 of the water samples, and it's very easy to see the shape of the distribution just by looking at the stem and leaf plot. Disadvantages, if you get a large data set, it can become challenging to have to make a stem and leaf plot. So what do we do when we have one of these larger data sets? We have another option here, which is to make what's called a histogram.
We'll do this on
And
page
with a
3.
histogram, you're going to use intervals of values and just figure out how many numbers you have in that interval of values. And so you'll see here the intervals are set up 0 to 10, 10 to 20, 20 to 30, and so on. Now one thing you want to be careful about is the endpoints. For example, the value of 10. The value of 10 should be put into this bar here on the left endpoint. And then if you had 20, it would jump into the next bar over here. Now, one of the things you can do with your
I'll
histogram
explain
is you
that
can
later.
change the width of the intervals that you're using here. And so in this next histogram, I'm using intervals of width 2 rather than of width 10. And you'll notice that they can actually change the look and the feel of the histogram quite a bit. So let's talk advantages and disadvantages of this one. As far as advantages, it is much easier to make a histogram if you have a very large data set. And once again, it is easy to see the shape of the distribution based on the histogram. Now, a clear disadvantage for the histogram is that we lose the information about every individual in the data set. So we don't actually know all of the 71 values for the water samples. We only know how many values are in each interval.
Okay. So let's go to the notes, bottom of page 2, where it says, here are long jump distances in inches for 2 athletes. Make a back-to-back stem plot with split stems and compare them. So there's a lot going on in that problem there. So what we're going to do, anytime you need to compare 2 sets of data, we've got 2 athletes. We've got athlete A, their long jump distances, and athlete B. Well, if you need to compare 2 sets of data in a stem and leaf plot, you're going to do what's called back-to-back. And so what we're going to do is we're going to have a middle column. I'll put some numbers in there in just a second. And then we'll have, let's say, athlete A. Those values will be on the left of the stems. And athlete B, we will display to the right of the stems. This is Mrs. Lewis. This, I do. No problem. Thanks. You called. Go get it. Okay. Now look at these long jump distances. I see 3-digit numbers, okay? Now you're only ever allowed to put single digits on the outside. The leaves can only be a single digit long. So that means we're gonna have 2 digits, the hundreds and the 10 spots inside. And I think it's a good idea. Let's find the very, very lowest number out of all of the data and the very highest number in all of the data. It also tells us in the notes, we need to be drawing back to back with split stems. So I'll explain all that in just a second. If you're searching through there, can you find the very lowest long jump distance? 151 is going to be the lowest. And what's the highest one you see? I thought that too. There's one higher. 187 is actually the highest. So I need to take that into account because my stems are going to go from 15 to 18. Again, that's the hundreds and the tens digits. But I need to make sure I split them. So we need to do this. We need to do 15, 15, 16, 16, 17, 17, 18, 18. We're splitting the stems. On the first row of each stem, we'll do the last digits, the digits in the one spot, from 0 to 4. The second row will be digits 5 to 6. Now, you have seen only stem plots probably in your life going this direction. So maybe you want to start with student B just to kind of get your bearings because student A is going to be kind of the mirror image of that and it gets really weird. So I'm going to start with athlete B and I'm just going to kind of scan through there and look at all the 150s and find the lowest one. Looks like 152 is the lowest one, and then I suggest marking through numbers as you plot them. So we does athlete B have 151?
Oh.
That's okay, these are great questions, okay? So I'm gonna do athlete B and athlete B only over here. And then it looks like there's 153, and we have to go in ascending order, least to greatest. It looks like there's another 153. Now I'm cheating a little bit, you guys, so because I've already done this before, so we can kind of speed it up a little bit. Then there's 157, which again, 0 to 4 is on the top row, but now 157 belongs in the second row there of the stem. There's 3 158s. 58, 58, 58, and 159. And then we go to the 160s. Two rows of the 160 numbers. If you can kind of line up your numbers the best that you can, it'll be easier when you're asked to describe the shape. It'll be easier if you've stayed a little bit more organized. That athlete didn't have any numbers in the 170s or 180s, so those stems are just going to remain blank. I always like to just go back and count and make sure that I've included all of the data values. $22. Okay. I started with athlete B just because that's kind of what we've done before in some previous math classes. It's been a while. You have to think just a tad when you go out to the left because you are still going to do descending or ascending order, but it's from the stem outward. So I don't want anyone to miss this. Take a pause if you're still on athlete B. You can go back to it in just a second. Let's look at athlete A. So we need to do that 151. That's the lowest. So I'm going to put my 151 hugged right up next to the stem, and I'm going to go out to the left from least to greatest. And we've got 154. And then I'm ready for, I see 157, so that's going to go in the next row, and then 159. So I think now that you've kind of seen me get started on that, you can finish this out. And doing this back to back just kind of helps us be able to compare these, which we are told that we need to do. So we're going to write some comparison phrases for athlete A and B. Oops, I did not mean to do that. All right, so you've had a little bit of practice, split stems, back to back, all together in one big example. All right, now you only need back to back if you're comparing two things, two individuals. So when we looked at dot plots, it was kind of easy to describe like shape, if it was skewed, if it was unimodal. Well, there's a really easy way to kind of make these stem plots look similar to those dot plots. And you can do that by just rotating your paper like this. And those are essentially like your dot plots now, okay? For athlete A, you turned it on its side, it would kind of look like this. So I just want us to kind of share, it says to compare them. So let's talk about shape. Let's be sure that we're comparing. Again, you don't want to just tell me the shape of athlete A and tell me the shape of athlete B. You want to compare them. You can say same, similar, different, something like that. What do you think about the shape? What would you assign as the shape to athlete A? Would you say roughly symmetric, skewed left, skewed right, uniform if it's straight across? What do you think? I honestly think it's roughly symmetric. I know that this little part right here is going to bother some of you, but it's roughly symmetric, I would say, versus I think this is slightly skewed to the left, okay, because you can see that there. So I would say that the shapes are different, and then let's put some context to it. If you were writing this down, I would say that athlete A, the shape of athlete A's long jump distances is roughly symmetric. Athlete B's distribution of long jump distances is roughly slightly left skewed, so they have different shapes. What about, let's not talk about, what about outliers, unusual features? Do you see any unusual features for either athlete? See any outliers, gaps, anything weird? If you do not, then you need to say that you do not. Don't just skip over it. Let the AP grader know that you checked for that. There doesn't appear to be any unusual features, outliers, gaps, etc. for long jump distances for either athlete. Center, if we're kind of just looking at, if we're thinking of center as the middle, it looks like athlete A might have a slightly larger center somewhere right in here than athlete B, or maybe you could debate it and say, well, it looks like they have roughly the same center. We're going to be more descriptive about that in a little while. And then, which athlete has a higher variability in the distribution of long jump distances? A has a higher variability of distribution of long jump distances. So that last little part that I'm saying, that's the context that I keep telling you about. I'm open to learning how, but I don't yet.
Do you have one that you can use?
I do, but it's one of the old. It's the teacher one.
Okay.
So, I could use it.
If you want to, I'll order you our server. Because apparently the department has to order this
Okay.
instead now, so it's.
Okay, I mean, I'm happy with getting everything I can, so if one technology doesn't work, I can use a different
Okay.
one.
I'll add it to my list.
Thank you.
There is a trial on there, if you just search air server, there's a trial that you can use now.
Okay.
Because I don't know how long it will take.
Okay, thank you for doing that. Go ahead and turn the page, page 3. We're going to change things up just a tad here. It says the following table presents the average points scored per game, PPG, for the 30 NBA teams in a recent season. We are not going to make a dot plot to display that data. We are going to practice the concept of making a histogram. When you make a histogram, you are going to be putting these numeric values into bins or buckets or categories. Okay, you'll hear people describe them those three ways. What that means is we're going to group things together. We're going to group points together so that we're not having to plot each and every individual team. So you kind of need to think about what it might be appropriate to count by. Again, it's good to start by looking at for the lowest and highest values in the quantitative data. So what's the lowest PPG that you see? Yeah, those poor Chicago Bulls, man. They used to be the dream team back in my day. All right, highest PPG?
Nuggets.
The Denver Nuggets. Doesn't seem likely, but okay. All right. So I now know I need to go from about 93 up to 106, at least. Now you can go past those values. Do you see a higher one?
Well, there's like two the same number that are like the lowest ones.
There are a couple of 93.2s.
Well, there's one other one. Doesn't matter.
That's okay. That's all right. So yeah, so say these things out loud. It's okay. I'm just kind of deciding right now what I need to cover in my graph. So as long as I go all the way down to at least 93.2 and up to 106.1, all the teams will be included. Okay? I think it's a good idea to kind of organize your thoughts into a table so that you're clearly describing what your bins or categories or buckets are. And so I'm just going to make a table here. This is not the histogram. This is helping me organize my thoughts for the histogram. You have two options when you make a histogram. You can make a frequency or a relative frequency histogram. What's the difference in those two phrases? Frequency versus relative frequency.
Frequency.
What are you going to say?
It's kind of like frequency is measuring like the amount, and relative frequency is like the proportion or percentage.
Okay, exactly. And what did you say, Christian? Same thing? Frequency is just a count of how many. So if I was making a frequency histogram, my bars would go up to how many teams were in that category. If I made a relative frequency histogram, my bars would go up to the percentage of teams or the proportion of teams in that category. When I did it before, let me just show you. I made a relative frequency histogram, and I'm not like wild about it because the stacks were all kind of short. I mean, you have to go up to 100%, right? Because percents are always out of 100. So I want to change things up. I'm just curious. I want to do with you a frequency histogram here. So let's just say frequency, which again, once we figure out our categories, we'll put how many teams are in that category. It's a count of how many. Let's make if we need to go from 93-ish to 106, what do you feel would be appropriate to count by? Yeah, integers, we'll count kind of ish by integers. I'll explain more in just a second. But you want to count by 1s, 2s, 5s. The rule is you need at least 5 bars on your histogram, so you need at least 5 groups of numbers. So let me show you, let me put this one back up on the screen. I chose to count by 2s. And it gave me 1, 2, 3, 4, 5, 6, 7 different bars. So this would be pretty spread out. If you feel comfortable doing that, let's count by 2s, which means I'm going to go from 93 to everything. Now, I can't just put 95. I need to put less than 95. Here's why. 93 all the way up to everything less than 95. If a team scored exactly 95, then we wouldn't know whether to put them in that bin or the next bin if we hadn't specified less than. Where would 95 go now? Would it go in the top group or the bottom group that I have here? The bottom, okay? So histograms, we have to think about boundary values so that we know where to put the teams in their correct bucket or bin. Go ahead and keep doing this. Follow the pattern all the way up until you get to at least 106. We have to cover all of the data. hardest part, you guys. Now you're just gonna count. Now be careful. It says that there are 30 teams distributed, so this frequency column, we've got to make sure in the end that the numbers add up to 30 teams, okay? That way we'll know if we've missed one. I think it's smart to kind of cross them off as you count them. I want you to tell me, and let's help each other out. The first person that thinks they have it, say it out loud so someone can verify. How many teams would go in the first bucket or bin? 93, anywhere from 93.0 all the way up to 94.9, I guess?
I got 9.
You got 9 already? Okay, we'll wait for somebody to verify here.
Yes, got 9.
Okay. All right, we're going to go with 9. That's the frequency. That's how many. 95.0 to 96.9. How many are we getting there? I got 5 as well. Okay, very good. Okay, 97.0 to 98.9. I got 5 on that one as well. Okay. 99 to 100.9. I only got 2. Chelsea, did you get 2? Did I count wrong? Tell me if my numbers look wrong to you. Again, there's a team right at 103.0. You've got to know that they go in this bin right here. 103.0 is included in this group. Take a second, add them up. Woohoo, got them all. Now we actually draw the histogram. So draw a horizontal axis and a vertical axis. We need to title those. This is going to be average points per game. This is going to be frequency. There is a time and a place where you want to use relative frequency. We'll talk about that in just a second. $93, $95, $7, $99, $101, $103, $105, $107. My frequencies over there in purple go from 1 up to 9, so I think I'm just going to count up to 10. Get your axes scaled and titled and situated so that we can just do the last little bit, which is drawing the histogram itself. And if you understand the categories, the boundary values here, then you'll know exactly what you're about to do. I need to draw a bar that goes up to 9 for the span of points from 93 to 95. So I need to go all the way up to 9. And even though if you were to look at a graph and have a multiple choice question on it, you were looking at a histogram, you would have to know that 95 does not belong in this bar, even though this bar is touching the 95. 95 would go in the category to the right. That's going to go all the way up to 5. So the bars are touching each other in a histogram. That's a difference between that and a bar chart. And these, again, actually show spans of numbers. This actually ended up being less work than the relative frequency one as well. So I'll probably just go with this in the notes for the other classes as well. That's how you create a histogram. I want you to at least have done it once in your life. You may have some more practice in the homework, but you're not going to have to draw a histogram on the AP exam. But if you've drawn one and you understand how to construct it, then you're going to be able to read them better. Let's move on and answer some questions, and then we're going to switch gears to talk more about center and how it's appropriate to describe center, because I keep saying we're going to get to that. When making a histogram, do bars need to be equally wide? Yes. It's called class width. And one thing I haven't said, so I told you these are bins or buckets. They're also called classes. So class width needs to be the same. You don't want to violate that area principle we talked about in your graphics. When it says, what about boundary values? I just want to mention something here. So our data, was our data for points per game continuous or discrete? Ooh, those are old vocab words. Continuous or discrete? Continuous. There were in-between values, right? So how in the world would you do this for discrete? I want you to make a little note. Histograms of discrete values. Histograms of discrete values. Center the bars above each possible value. Center the bars over each possible value. I'll show you what I'm talking about. Let me give you a chance to write that. If you want to make a quick sketch, here is what I'm talking about. So if you had discrete values like, 1, 2, 3, or 4, and you made your classes and you wanted to show the heights of those, it's going to center the bar around that so you know that only 1 is included in that bar. Only 2 is included in the second bar. So it's a little bit different visually than if you have continuous data. I mean, this one's probably obvious to you guys. How is a histogram different than a bar chart? The answer, though, may not be as obvious. Bar graphs are for categorical data. So we draw bar graphs where they're all separated out when the data is words. Like if I were to survey you and your answer was yes or no, or it was what is your favorite season of the year, and I wanted to graph that with frequency or relative frequency, I would use a bar chart. We use histograms for quantitative data. Okay, hugely important. And you might have noticed this can be a little bit deceiving, like when you took your 1.1 quiz. You always have to look at that vertical axis. Are they using frequency or relative frequency? Why would we prefer to use relative frequency, percentages, proportion? And it's when you're comparing groups of different sizes. An example would be if I wanted to look at the distribution of GPA for our class, just us in here, versus the entire school, and I wanted to compare those distributions, I would want to look at percentages, part of whole, proportions, not just how many of you in here have an A, how many of you in here have a B, not the frequency. If you have groups of largely different sizes, then you want to use relative frequency. Some of the common histogram mistakes are forgetting to label and scale your axes and not reading boundary values correctly. That's kind of where one little part of the chapter ended, and now we're moving into something that's going to feel completely different, but it is all tied together. We're going to talk for the rest of the notes about center. What are different measures of center? How do you figure out what they are, and which one is most appropriate if you're having to describe in a paragraph the center of a distribution? Which one do you choose? This says, how do you calculate? That little symbol right there is called X bar. Statisticians got really creative when they named things. It's the X with the bar over it. It's X bar. And all that is the average or mean. On your yellow formula chart that is going to maybe intimidate you the first time you look at it, the very first formula on there is the formula for X bar, for mean, sample mean. And it looks really scary, but you learned back in elementary school or middle school to take the average, you add up all of the values, you find the sum, that's what that big sigma symbol is, the sum of all of the data values, and you divide by however many there are in the data set. That's all this fancy stuff is saying in mathematical symbols. Both of those, if you do 1 over n times the sum of all of the data values, that's the same as finding the sum and then dividing by how many there are. Now, before you turn the page, I want you to know the difference between, there's a couple of symbols that both mean average. X bar is a sample mean. It's the mean of a sample that's taken from a population. Mu, like a little kitten sounds, that is the mean of a population, which is, in general, it's harder to find that value unless you're working with a pretty small population, okay? That's the difference between those symbols. That will become really important later on. But for now, we're going to stick mostly with X bar. That's the difference. Okay, next page. This one's going to be easy for you to remember. What's the difference between a statistic and a parameter? I want you to think of salt and pepper, S&P. Statistics describe samples, SS. Statistics describe samples. Parameters describe populations, S&P, salt and pepper. The S's go together. The P's go together. Statistics we use to describe sample data. Parameters are what we use to describe entire populations. Parameters are a little bit harder to come by, and that's why little stars next to it there. I wrote statistics help us estimate parameters. Sample data helps us kind of predict or see some kind of pattern going on in the overall population. That's why statistics are useful. What is a resistant measure? We're going to talk about measures of center that are resistant or non-resistant. Next time I see you, we're going to talk about measures of variability that are resistant and non-resistant. A measure of something is resistant if it isn't sensitive to extreme values. It's like hardcore. It stays put. Outliers aren't going to affect it. A measure is resistant if it isn't sensitive to extreme values. Or you can just put outliers. Outliers don't really have an effect on resistant measures of center or resistant measures of variability. It says, is the mean a resistant measure of center? No, it is not. That's the weakness of using the mean. If you've got outliers in your graph, the mean is going to be pulled in the direction of those outliers. We're going to illustrate that in the notes, so if you didn't quite get that, it's okay. But the mean is not resistant. Well, then why would we ever use it? We'll see in just a little while. How can you estimate the mean of a histogram? It's going to be usually like near the tall stack. It's not my favorite thing to do, trying to describe the mean of a histogram. But you're trying to kind of find the taller group of stacks. So we've got mean, that's the average. That's one way you could describe center. The other way you could describe center is the median. Before I uncover this, how do you find the median of a bunch of numbers? It's the middle number, but what must you do first? My on-level kids forgot to do this on their quiz the other day. What do you have to do with your numbers before you find the middle one? You gotta put them in order least to greatest. It is the best thing ever in the universe when the numbers are already in order for you. But, so you just find the middle one. That's easy if you've got an odd number. What if you have an even number of data values and you need to find the middle one? And there is no middle one. You know what to do. You just find the average of them, I think somebody said. Add them up and divide by 2, somebody else said. That's exactly right. You may not need to write any of this down if you're like, I know what a median is. These are your notes. If you are very comfortable with that, then don't even write anything down. But if you have an odd number of values, the median is just smack dab in the middle. If you have an even number of values, the median is the average of the 2 middle values. Pretty easy stuff. Mean and median, both measures of center. Well, when you're asked to describe a distribution and you get to the part in SOX that's center, which one do you talk about? And it has to do with which one is resistant versus the graph that you're actually looking at. So the median is resistant. The median is going to stay put and not be as affected as mean is when you've got outliers. Okay? Now here is what I think I want to do on this very last one. I think I want to illustrate for you. You can draw these pictures together. How does skewness and outliers affect the relationship between the mean and the median? And then we're not going to play around with that applet. I think this illustration will be just fine, okay? When you have mostly symmetric data, roughly symmetric, mostly symmetric, you can see that it's single peaked. Your mean and your median are both going to be pretty much in the same location. Now let me be a little bit more. There would be a horizontal axis. We're talking about the number line here. Mean and median are going to be the same. Usually a little triangle will be pointing to the mean. The median will typically be a bar. I'm going to put mean equals median when things are symmetric. They're the same. If you are looking at a distribution that's pretty symmetric and has no outliers, you are going to choose to talk about, the mean, because the mean is not affected by those things. So the mean is going to be your choice to tell me about. That's the measure of center you would describe to me if your distribution, your dot plot, your stem plot, your histogram is mostly symmetric. If you have a skew, let's say skewed left, these are very rough sketches. Okay. Your median is going to be somewhere kind of near the peak. But if you have outliers, your mean is going to get pulled in that direction because it is non-resistant. And so your mean would be somewhere closer, not necessarily extremely far away, like I kind of drew it in an extreme way there, but your mean is going to be lower than the median. That's the point of drawing this. In a left skewed distribution, the mean is going to get pulled towards the outlier. So if you have a skew, you want to tell me about the median. That's your option. That's your choice there. And just to add, the mean would be less than the median in a left skewed graph. The mean will be smaller than the median if it's skewed left. Now, if you had a multiple choice question and you didn't have a picture to go along with it, you might sketch a left skewed and kind of remind yourself, oh, the mean, it's non-resistant, it gets pulled to the left, which on a number line, smaller numbers are to the left, so the mean must be smaller than the median. You know exactly what I'm about to do. I'm going to draw a right skewed graph. We're going to label all the stuff. And we're pretty much going to wrap it up, so we've got time to log on to AP Classroom here. The median, again, is going to be near that peak. But in a right skew, well, bigger numbers are to the right, your mean gets pulled in that direction. So the mean in a right skewed graph is going to end up always being larger than the median. Maybe not by a whole lot, but it is going to be larger. Again, in any sort of skewed situation, the correct measure of center, listen to all that vocabulary, the correct measure of center to describe is the median. If you're dealing with mostly symmetry, then describe the mean. Tell me about where you think the mean is, the center. Or if you can, actually calculate the mean. Add them all up and divide by however many there are. Okay.